second HCI at KAIST seminar. I'm Juho Kim, and I have two quick announcements to make. So right after the seminar, starting at 5, we're going to have some pizza and cookies and drinks. But we're going to do it in the room next door. Because last time we tried it here, it's not really interactive. It's hard to actually talk to each other. So the room right next door has round tables. So please sit around with people you don't know and introduce yourselves and mingle. And we'll maybe force you to talk to other people as well. So that's one thing. And the second thing is Professor Im Yoon-kyung in Industrial Design asked me to make the announcement on her behalf. The Industrial Design Department marks its 30th anniversary next week, and they have invited 10 plus world-class designers and design researchers to come and talk about design and design education. It's free for all, open to the public, and she'll actually send more detailed announcements later this week, I heard. So please check it out, and it's another great opportunity to listen to these great people. Okay, so now I want to introduce Professor Krzysztof Gajos from Harvard University. He's a professor in the School of Engineering and Applied Sciences. And he's been doing a lot of really exciting stuff, but when I think about his work has a lot of these attributes that great HCI systems work often has, which is he identifies and introduces a set of techniques or mechanisms or algorithms to tackle practical and important real-world problems. So that includes people learning with videos at scale, or brainstorming for ideas in a collaborative and creative setting, or participating in experiments to help science. And some of the other stuff will be actually the main focus of this talk today. And his secret sauce is by basically bridging AI and HCI. And I think this really interesting combination makes his work really exciting, and we'll get to hear some of it. I had the pleasure of working with Krzysztof as a PhD student from 2010, and it's been a great time. And he asks really deep and sharp questions, and now it's our turn to ask these questions to him. Before Harvard, he had his PhD degree from the University of Washington. He has his master's and bachelor's degrees at MIT. And we're really lucky to have him for the entire week, and this is very unusual, and really we're thankful that he committed to coming to KAIST and spending time with us. So take it away.
My name is Krzysztof, and it is an enormous pleasure and honor to be here. I feel particularly connected to KAIST because several people that I've known for a very long time and that I feel very close to are here. So many of you know that I've known Juho, but I'm not sure if you know that person Alice was actually one of my first collaborators ever. In 2001, when she was a graduate student at MIT, and when I was still trying to decide what to do with my life, she invited me to be part of a study that she was running, and it was the first time I ever participated in a quantitative human subjects experiment, and I learned a lot from it. So thank you very much, Alice. Juho has been one of my most recent collaborators. We published several papers together, but this is probably one that I am most proud of because it introduced the concept of integrated crowdsourcing or organic crowdsourcing. We still haven't decided how to call it. But the idea is that we want to bring the benefits of crowdsourcing to volunteer communities. And in most volunteer communities, when you want to accomplish something, there's exciting work to be done, and there's also some tedious work that needs to happen that nobody wants to do. And in learner sourcing and in more generally integrated crowdsourcing, we're figuring out ways to integrate this tedious, boring work into the exciting tasks that people want to do. And we believe that crowdsourcing is a very powerful tool that we can bring to volunteer communities because crowdsourcing solves the coordination problem. It allows people who only have 5 minutes to contribute to work together and accomplish something very big. Over the past 3 days, I've met many people who do very interesting HCI work here at KAIST. You've got a very large and very vibrant community, and I'm very jealous of it, because at Harvard, I am the HCI department. And these are some of the people I work with. But there's only one group at Harvard whose primary focus is human-computer interaction. And because of that, we actually cover a very large number of topics. With Juho and with others, I worked a lot on education and systems that help people learn. Our first project was on helping people learn how to detect landmines. You know what landmines are? Somebody can say it in Korean? Yeah, right? You step on it, it will so finding it is actually very difficult, and we've built a system that helps people learn that skill much faster. And this is very important because when NGOs come to Cambodia or Laos to help remove landmines, they do not bring deminers. They bring instructors, and they hire people from local population and they teach them how to detect landmines. So it's very important that people can be taught very quickly and very well. We also work a lot on crowdsourcing, and in particular, as I said, on figuring out how to use crowdsourcing techniques to help volunteer communities. I'm also very excited about changing the methodology of empirical work in human-computer interaction. So many of you have conducted studies in the lab. You know, the first 5 participants, that's exciting. The second 5 participants, that gets tiring. When you get to 20, you cannot remember who was who, right? So we are trying to see, can we have other ways of conducting experiments in HCI? And one of our most exciting systems is Lab in the Wild, which you can visit after this talk, labinthewild.org. It's an online laboratory, and we've already had more than 1 million experiments completed, and it really transformed how we do research. It does not completely replace traditional laboratory studies, but it is a very valuable complement. And I'll visit the crowdsourcing class tomorrow, and I'll talk a little bit more about it there. But the work that I am going to talk about today has to do with kind of my oldest interest, which is building systems that automatically adapt themselves to people. So this is work that Juho has not seen much of, so it will be hopefully interesting to him as well. And I would like to show you 3 projects in that space. But before I do it, I kind of want to set you in the mood and kind of help you understand what kinds of problems we might have with the current design practice before I show you the adaptive and personalized solutions. So, to set the mood, this is a very iconic design, Swiss Army knife, right? It's so iconic that we even use it as a metaphor. So, you know, when you encounter a very versatile and powerful, simple piece of software, you say, you know, it's a Swiss Army knife of text editing. You say it's Swiss Army knife of image manipulation, right? So this is a tool that I've owned for a very long time, and I loved it. Until in 2008, I went to the KAI conference in Italy. I had a room in a very cheap place, but it had a very nice roof deck. So one day, I invited all of my friends. We came up to the roof deck, from which we could see the entire city of Florence. We had a couple of bottles of Chianti, but nobody had the opener. So before next conference, I got a slightly better Swiss Army knife, and I was prepared. But on my way to the airport, my suitcase broke, and I needed a Phillips screwdriver to fix it. I somehow patched it together with wire, but before the next conference, I decided to add it. And since then, they've come up with the version 4.0. It's real, you can have it. So I think you are seeing what's going on. As we start with a Swiss Army knife of text editing, Swiss Army knife of image manipulation, and then customers call in and say, I want this, I want that, I want that. And very slowly we arrive at better systems that essentially are unusable. So really what we want, like what most of us want, is something at this level of complexity. The trouble is that each one of us wants something different, but at this level of complexity. Because our current design practice is to produce one product that fits the needs of everyone, our products don't look like this, but they typically look like this. Of course, you may say, no, in computer science we would never do that, right? So I was an intern at Microsoft, and we looked at the usage data of Microsoft's Office, and most people use between 5 and 10% of the features in any Microsoft product, but every person uses different 5 to 10% of the features in those products. So, kind of the overarching thesis of my talk today is that this one-size-fits-all design, where we produce a single product to fit the needs and desires and abilities of every person, inevitably causes discrimination. In the sense that it makes it addresses the needs of some people better than the needs of other people, and often these differences are very systematic. And for the rest of the talk, I'll show you how with the one-size-fits-all design, we discriminate against people with motor disabilities, with color vision disabilities, and also we discriminate against people who have differences in what they perceive to be beautiful. And this is going to be a surprising result, but we'll get there. So these are the three topics that I wanted to show you, but before that, I would like to introduce you to the concept of disability and handicap, just so that we are on the same page. How many of you know what this is? Juho and Alice, of course. I wonder how many of you have visited MIT? Yeah. So this is the main entrance of MIT. It's really beautiful. You come up the steps, you enter, you come up to this door. This is one of the first ever automatic doors ever in the universe. MIT still has it. It's kind of an antique, but it's really, really awesome. And you go through these doors, and this is what you see. A beautiful lobby, really impressive, big, charming, beautifully designed. It feels great. Unless you happen to be in a wheelchair, in which case you approach MIT, and then you notice this little sign that says, go this way. The signs lead you to the entrance to the basement. Then you enter this really dark corridor with no signs. If you are lucky, you eventually find your way to the slowest elevator on campus. And you take this elevator up, and it dumps you in the darkest corner of the lobby. Contrast this with the design choices made at one of the buildings at Harvard. No, Harvard also has badly designed buildings. But notice, so this is the regular entrance, but this is the accessible entrance. So this ramp is right next to the regular entrance. It leads to the same door. It's aesthetically pleasing. So a person in a wheelchair who approaches this building with their friends will naturally go together with their friends along the ramp. Everybody will go together. They will be part of the community. They'll be having the same experience. Whereas at MIT, they would have a very different experience from everybody else. Everybody goes, through these beautiful stairs through the beautiful lobby, and the person in a wheelchair goes through the basement and maybe or maybe not eventually makes it inside. So, with these two examples in mind, I would like to introduce the concepts of disability and handicap as defined by the World Health Organization. So disability, you have disability if you cannot perform a particular activity. So if you cannot write, if you cannot enter a building, you are disabled. You are handicapped if some difference in how your body functions causes you to not be able to participate in social activities. So if I'm not able to attend a party, if I'm not able to enter, to have the equal experience of entering MIT with my friends, then I'm experiencing a handicap. Notice that disability and handicap are not just a function of my body, they're a function of my body and the function of the design. As designers, we have the power to introduce disability and handicap, and we have the power to remove it. And I'll be arguing throughout this talk that the way we design things causes us to inadvertently but systematically introduce handicaps throughout our digital life. So kind of to summarize, people entering MIT experience a handicap, people entering MIT on a wheelchair experience a handicap, whereas with a different architectural design they do not. So I'll be arguing over and over again that when we design resources, whether physical or digital, it's not enough that we make it possible for people with some differences to access that resource. We also have to make sure that this access is equitable. Equitable is a difficult word or uncommon word in English. It means kind of equal, the same. You get it, right? All right, so with this background behind us, I would like to introduce the first technical project in which we addressed the needs of people with motor impairments, so motor disabilities, people who have difficulty moving their hands in particular. So I would like to begin by telling you a story of Ken. Ken has spastic cerebral palsy. It's a condition that happens at birth, and it means that he has very little voluntary control over his arms. They flay. He can make very large, rapid movements, but very, very inaccurate. His speech is also impaired, so he cannot speak very clearly, so he cannot use speech recognition software. So instead what he does, he uses his chin, this is his chin, and he controls a trackball with his chin, like this. He also has a little stick attached to his head, and he uses it to peck on the keyboard. So despite his disability, Ken has a computer science degree, and he has his own computer science consultancy firm. But he takes 3 times longer to perform activities on the computer than everybody else. So even though he's highly educated, and even though he has a very marketable skill, he lives in a very poor home, in a very poor neighborhood, because he cannot do as much work as everybody else. Claire, on the other hand, has muscular dystrophy. So it's a disease with which she was born, and it means that her muscles are very, very weak. She needs to use both of her hands just to use the mouse. She can make only very small movements, but she can make them very accurate. She can scroll, and she can move accurately, but she cannot make big movements. And Claire is a student, and her problem, the challenge that she's experiencing is that she can use all of the software that is needed for her classes, but she's also much slower using that software. So when she takes the same number of classes as everybody else, she doesn't have enough time to finish her assignments, so she gets poor grades, not because she's not working hard, or because she doesn't have the mental capability, but simply because she doesn't have time to finish the work. If she takes fewer classes, then in America you only get 4 years of financial aid. So if she takes fewer classes, her financial aid will disappear before she can finish her degree. So in either case, Claire is at a professionally disadvantaged position at the very beginning of her professional life, not because she's not diligent, not because she's not smart, but because she's much slower with today's software than her peers. All right, so we've got 2 examples of handicap. Ken earns very little because he's got the skills, but he cannot perform them quickly, and Claire cannot get either good grades or a good degree because, again, she's slower with the software that she's required to use. But when we look at the reasons why they're slower, we see that they are very trivial. So Ken has very hard time using pull-down menus and these very tiny interactors like the spinners. But he can do everything else very fast. So he can click on buttons, he can navigate through the user interfaces, but it's these very small selections that are very difficult for him. Claire, on the other hand, can do all of these small things very well, but she has a very hard time making large movements. So in this UI, there are tabs at the very top, so having to perform actions over here, then move up and then move back down, that's very difficult for her. And again, making movements all the way to the bottom, to the buttons, takes her a lot of time. You may think, well, what can we do? I mean, they're disabled. Disabled means that you cannot do things very well. But when we create manually user interfaces for them that just required of them that they do the things that they can do well, so Ken can make large movements to large targets very easily, and Claire can make small, accurate movements very easily. If we design user interfaces for the things that they can do, they suddenly become very efficient. So the problem here is that the designer assumed that one of regular able-bodied people will be the user, and there is a mismatch between what the designer assumed and what Ken and Claire can do. So the reason why Ken and Claire are handicapped is not inherent to their physical ability. It is only a result of this mismatch between what we assume and what they actually can do. So this implies that for people with very unusual abilities, we need different interfaces. And it's not that we can create just one disability interface. We need different one for Ken, and we need different one for Claire, and we need different ones for people with different abilities. So we need lots and lots of interfaces. And as a computer scientist, I claim that if you need lots and lots of something, you cannot really ask designers to do it by hand. Let's try to automate it. So if we want to automate design, the first thing that we need to do is try to understand what design is. So I talked to my computer science colleagues, tried to figure out how they think of design, and many of them conceptualize design as a process in which you come up with a description of the problem, then you hand off this description to somebody really smart, and a week later you get something awesome. And this is actually a very common way of thinking about design, so common that in design literature there is even a name for it, and it's called design by genius. But if you actually ask the geniuses, I mean the designers, how they do design, they tell a very different story. So they typically start by enumerating many possible designs. So they're given a problem and they come up with many possible designs. Then they try to think, is this a good design? Is this a good design? They try to think what makes one design better than the other. And once they've figured that out, once they've seen a range of possibilities, once they've understood what it means for a design to be good, they slowly start narrowing down this design space until they come up with something that they're fairly sure is better than the alternatives. Now, they call it design by exploration, but notice what it is. We are enumerating possible solutions, we are assigning a value to each of the solutions, and we are picking the best. Any engineers in the room? Computer scientists? Do you recognize this process? What do you recognize it as? What does it sound like?
What's his name?
Software engineering.
What?
It's
A computational process. Enumerate options, assign a value to each, pick the best. Who said it? Yeah, doesn't it sound like optimization? So let's actually think of design as an optimization. In fact, Herb Simon has a whole chapter in his Sciences of the Artificial where he argues that design process is really optimization. So again, notice what we are doing. We are trying to figure out all possible designs. Then we are trying to figure out how good every design is. And then we essentially have to pick the best. And, well, we better do it quickly. So how did we do it? First, to enumerate all possible designs, we conceptualized, we represented applications in terms of the types of information that need to be exchanged between the application and the user. So in our representation, we thought of the leaf nodes as the individual pieces of information that needs to be exchanged. For example, intensity of the light, or whether the light is on or off, all the selections and so on. And the interior nodes of this representation correspond to semantic groupings. So things that should be together in the interface are represented in this abstract representation by belonging to the same interior node. Then somehow we enumerate all of the ways in which a particular type of information can be communicated using our UI design language. So the next thing that we had to do is figure out how to assign value to each possible design. And there are many ways of thinking about what makes a user interface good. But for people with motor impairments, people with disabilities, the biggest issue is that the bad designs are very slow to use and good designs are fast to use. They don't care whether it's pretty, they don't care about anything else. They really want things that work, that are efficient. So for this particular population, our cost function is a prediction of how quickly they can perform a typical set of operations with that design. And to make it possible to computationally predict how quickly people will use a particular design, we first asked each person that we worked with to perform a set of diagnostic tasks. Then we used machine learning to build a predictive model of how well they can perform different basic operations. And from that, we would, for any candidate design, we would be able to say, this one will take 41 seconds, this one will take 50 seconds, this one will take 36 seconds. So we're able to make these predictions. Now, the last challenge is that now that we've been able to enumerate all of the designs and we're able to assign a value to each one of them, we have to pick one the best quickly. And this is challenging because even for relatively simple applications that we worked with, there were up to 10 to 17 different possible designs that we could produce. And just in case it wasn't clear, 10 to the 17 is a very big number. So even if we could test 1 million designs per second, we would still need over 3,000 years to test 10 to the 17 designs. At first I thought, great, I was a graduate student, it sounded like job security. But my advisor told me that graduate students don't get tenure. Instead, we used several techniques from artificial intelligence. The two that were most powerful were the branch and bound algorithm that allows you to prune out, to completely ignore parts of the design space that are provably less good than the solutions that you have already found, and complete constraint propagation, which allows you to very quickly eliminate solutions that are provably infeasible, solutions that will not fit on the screen. So with these two techniques and a couple other slightly less prominent ones, we're able to take this problem down from 3,000 years to less than a second. So what you see over here is the system producing new designs automatically, solving this entire optimization problem, in this case for different screen sizes. So this is happening in real time, and this is not an approximate solution, this is a complete solution. And this approach is very versatile. All you have to do is switch a different library of UI elements, and you can start designing, the same algorithm will design user interfaces for very different devices. You can tell that I started on this project a long time ago. This is a WAP phone. You know what WAP is? It's a protocol from many years ago. And this approach works well for data-intensive applications with many different windows and components. It also works very well for highly interactive applications. So it's quite versatile. So we applied this system to automatically generate user interfaces for people with motor impairments. And let me show you how it works. So this is one sample interface that we reproduced from a popular application. This is what it looked like in the original application, and then we asked our system to generate user interfaces that were functionally equivalent, but that would work well for Ken and Claire and 15 other people that were part of our study. So this is what Ken's interface looked like. You will notice that the spacings between elements are quite large, so that he can hit them reliably. All of the buttons are large, but there are some trade-offs. The larger we make these elements in the lists, the more need for scrolling there is in the user interface, and scrolling is very difficult for Ken. So we cannot grow these things infinitely big, because if they're too big, then he would need to scroll, and that's difficult. The user interface is still divided into 3 tabs, but that's perfectly fine for Ken, because he can make these large movements to the top without any problem. In contrast, this is the design that the system automatically generated for Claire. Notice that here there are no tabs. Everything, all of the functionality in a single window, so she doesn't have to make these big movements to the top. There is lots of need for scrolling in many places, but that's perfectly fine because she's very good at using the scroll wheel, and everything is very tightly laid together. So what you will notice is that the design for Ken is very different from the design for Claire and vice versa. The design for Ken would be a killer for Claire, and the design for Claire would be impossible to use by Ken. So again, what we see over here is, first, if you design user interfaces for a person's specific abilities, it looks like it's possible and you can actually really address their needs. And also, there is no such thing as a single universal design. You cannot design a user interface that will work for both Ken and Claire. It's simply impossible. So we really need to take these people as individuals with their idiosyncratic, unique needs and abilities and design for them individually. And for that approach to scale, we really need to automate the design process. So some numbers. What you see in red over here, this is how long people with disabilities took to perform a set of standard tasks with standard user interfaces. In green, you see the amount of time that people with able-bodied people, normal, regular people, took to perform the same tasks on the same user interfaces. You will see that there is a very big performance gap. People with disabilities were on average twice as slow as able-bodied people. But with user interfaces that were individually automatically generated for people with disabilities, we closed most of this performance gap, right? So we made access not only possible, but we made it a little bit more equitable. So let me repeat kind of my main messages. I teach undergraduates a lot, and I find that if I say things once, they don't remember. If I say things 5 times, maybe. So I'll say things 5 times. So in one-size-fits-all design, we can never anticipate everybody's needs. We always assume something about our user, and we're inevitably discriminating against people who are different from what we assume. When we make access to resources, in particular digital resources, we have to make sure that it's not only possible, but we have to make sure that different parts of the population can access it equally well, that they can be equally efficient and that can have comparable experiences. And as a computer scientist with love for artificial intelligence, I believe that one way to accomplish it is to make sure that user interfaces adapt themselves to users, and not just users adapt themselves to user interfaces. So I want to make sure that if I am a little bit different, I will make some effort to adapt myself to a computer, but I want the computer to make some effort to adapt itself to me. So in the current world, we all use the same user interface. I'm doing well, but Claire and Ken are having a very hard time. In the adaptive world, everybody gets a different user interface, and we have a different tools, but we accomplish things equally well.
So, Mike, can I ask a question? So I disagree with what you just said, because you said equally well, but there's still that difference. Did you try to get rid of that gap at all, or does it work at all, or is there something you do better? Or?
I did as well as I could. I've run out of ideas. So yes, there's still work to be done, but I closed 62% of the gap.
I'm not saying that you didn't do a good job. I mean, I think you've done an excellent job, but I'm just wondering if there are other things that
I'm sure that there can be, and maybe you'll be inspired to think of the ideas that I've missed.
So I mean, looking at the examples for, like the one on the left, for example, which was designed for Ken who needs big buttons. But if you look at the OK and cancel buttons, they're still quite small. Like they could take up. Is that a limitation of the UI language?
It was the limitation of the representation used to describe the problem. Yeah, I could have. There is a lot of unused space in this user interface. I could have added another step that would fill out, that would make use of this unused space. In the back.
So I was wondering, I mean, good design is more than efficient, but it's also like easy to understand or pleasing.
That would be the next two projects.
Okay, so I was wondering because this seems to be optimized for efficiency, right? But
because this was the biggest need of that particular population.
So I was wondering if AI can also make something that's aesthetically pleasing.
Yes, there are actually papers on that specifically, and I'll show you also how we can quantify aesthetics. One more question and then I'll move on.
So the able-bodied UI, you base that on the popular application, whichever one that is. If I, as an able-bodied person, were to take the ability test and use this, would I get the middle one there, or have you looked at what?
No, you would get something a little different.
Okay.
And you would be a little faster, but able-bodied people, it wasn't a very big gain, and able-bodied people did not like the personalized user interfaces. They thought they were ugly and not a big gain.
Okay.
Interestingly, people with disabilities thought, when we asked them how aesthetically pleasing were these interfaces, they thought they were beautiful. Like, able-bodied people thought they were ugly. People with disabilities thought, oh, they're so beautiful. It looks like if you really make somebody's life better, they'll fall in love.
They represent a solution to a problem.
Last question.
As a matter of fact, I have two quick questions. Is that okay? The first one is how you actually incorporate or in this case, CAN and the other person's laptop, two different types of handicapped people, and how you incorporate their disability into the automated generation of your user interface.
So let me answer one question at a time. So I asked each one of them to perform this set of tests. And I used the results to produce a machine learning model of what they can do. And that machine learning model was part of the objective function for the optimization. So I ran the optimization separately for CAN and separately with different models.
This is not a question, but your paper or whatever you published one actually justify why, for example, the three things actually figure out the user's need.
This was enough. This was there was one more activity, just repeated clicking. So there were 4 activities that I measured, and that was enough.
Okay. So my second question is just kind of cross check, because this is already 4:36 and 4:40, so we have the seminar until 5. So I was very wondering when you're going to talk about actual real optimization details, because you talk about already justifying the real-time, runtime optimization of your user interface depending on the user requirement. I'm really interested in hearing how you actually do that.
It's in the paper. I designed this talk for audience who may have more interest in design than in the optimization.
Okay, thank you.
Okay, so I've told you about this project. Let me tell you about color vision deficiencies, so color blindness. And this project was led by David Flatler and Katarina Reinecker. So we use color to encode information. I'm not sure how clear it is. Well, on this project it's not very clear, but in this part of the user interface, you've got messages alternating in red and green. For some people in this audience, this will be indistinguishable, even if the color was better, if it was displayed better. Some people see it like this. People with red-green color blindness cannot perceive the difference between red and green, and this is how they would see this image. So we would like to recolor this image such that they can perceive the differences between colors that are supposed to encode information. And such tools already exist, and if you run them on this system, this is what these systems will give you. So notice you can now see the different colors over here. You can see the alternating colors in the messages. This projector is not particularly bright, so you cannot see the details, but you can probably see the lines of alternating color. But notice something else. We use color not only to encode information, but we also use color to encode mood. It's actually a very important part of visual design. So the original design, it's about red, luscious lips. right? It's supposed to convey warmth. It's supposed to convey love, prettiness. But what you get in this design is more like, I don't know, Arctic kiss of death. So while you restored while we made the information differentiable over here, we entirely lost the message encoded in the color, the emotional message encoded in the color. So we would like to create recoloring systems for people with color blindness that would create something more like this. Use the colors that the person can see, but also use them in such a way that you come as close as possible to the original emotional message as possible. Again, we want to make sure that people with color blindness not only can access the color encoded information, but that the access is equitable, that they have similar experience to those of us who can perceive colors well. So the problem of recoloring is one that we can also think of as optimization. We take the original image, we take an individual model of what colors that person can see, and we try to come up with an optimal mapping between the colors in the image to the colors that the person can see. And without two elements in the objective function that prior systems considered. We want to make sure that the colors that were distinguishable in the original image are also distinguishable in the recolored image. And we want to make sure that, if possible, we use the same colors as in the original design, if the person with color blindness can see those particular colors. We extended this model to also capture the emotional content of the colors. So we wanted to make sure that the new design has the same emotional message as the original design as much as possible. So the first thing that we needed to do is quantify the emotion conveyed by the color in the design. And there's actually some very interesting work in psychology that argues that there are just 3 dimensions of emotional response conveyed by color. One of them is whether the color is active or passive. Another one is whether it's cold or warm. And another one is whether it appears heavy or light. And if you can capture these 3 things, you can construct any other emotional response a person may have to the color. So now that we've established that, we wanted to see whether people with color blindness have the same emotional responses to the colors that they can see as the rest of us. So we ran a study in which we presented them with colors, and we presented people with regular color vision with the same colors to check what emotional responses they would have. And we found that people with color vision blindness and regular people responded to the same colors the same way. So that was great. So using this new extended optimization approach, we built a system that would take an image like this one, which a person with color blindness would see kind of as gray washed out. This is what existing prior systems would recolor it as. But our system would produce a design like here in the bottom right that not only makes the information distinguishable, but also captures as much of the emotional content of the original design as possible. And we obviously evaluated our work, and we found that in terms of making the color-encoded information distinguishable, we did as well as previous systems, but we did much better keeping the design close to the original colors, and we also did much better at maintaining the emotional content. So again, this project was started with the observation that existing recoloring systems make access to information possible, but they do not make it equitable. So with our approach, people with different color vision abilities, when they get presented with the same content adapted to their unique abilities, have very similar experiences, not only intellectually, but also emotionally. So this was the second example, and the third example is perhaps...
So can you apply this to maybe like virtual reality? Can you say, because you know, they have difficulty, I'm sure, with physical objects.
Oh, I see. So essentially creating like an augmented reality experiences.
Yeah,
Because,
augmented reality.
yeah, because an obvious problem is that if you are red-green colorblind, you go to the market and you cannot tell whether the tomato is ripe,
Right.
right? Because red-green looks
Yes,
exactly the same.
yes.
Yes, that's if you can process fast enough, yes. Because solving this optimization problem actually takes a little bit of time, but it can be done fairly quickly. So
I have a related question. I saw somewhere that there's an Israeli company that's doing something that she mentioned. So
Oh.
I was wondering if this was related to their work or.
We know nothing about it. So there are quite a few recoloring systems on the market. Ours, improves on them by making sure that we encode the emotional content of the image. They haven't contacted us, but it's a well-established technology right now, recoloring. The trick is doing it quickly. So the last thing that I wanted to show you is perhaps the most surprising result. And one that you initially might not believe is a problem. So I'm going to argue that we differ in what we perceive to be beautiful, and that this is a problem for designers. And now pay attention to the screen because there's going to be a quiz. I'll show you an image for just half a second, and I'll ask you a question about it. Okay. How many of you found this visual design beautiful? How many of you would be willing to make a purchase on a website that looked like this? With your own credit card? Okay. There will be another quiz. How many of you found this design beautiful? How many of you would be willing to make a purchase on a page that looked like this? Okay. So it doesn't actually matter, which of the two things you preferred. But what matters is that after seeing a design for 500 milliseconds, you not only decided which one is beautiful and which one is ugly, you also decided which one you are going to trust and which one you are willing to use. Right? 500 milliseconds, and you created a lasting impression of what's trustworthy and what you want to engage with. And so perception of aesthetics impacts our sense of trustworthiness, it impacts our willingness to engage, and really interestingly, it also impacts whether or not we're going to be successful using the design. So there was a very interesting set of studies originally conducted in Japan and later reproduced in Israel, where people were presented with two designs that were functionally identical, but one was beautiful and one was ugly. People who used the beautiful design were faster and made fewer errors and recovered from errors faster than people who used the ugly design. We believe that this is because when we feel happy, when we feel positive affect, we are much more exploratory. So when we run into a problem, rather than banging our head against the wall, we try something different, we recover from errors much better. If we feel unhappy, angry, or experience negative affect, we just do the same thing over and over again, which makes it very difficult for us to recover from errors, to be creative. So whether or not we perceive something as beautiful impacts our sense of trustworthiness, our willingness to engage, and our ability to succeed with a digital resource. So now the question is, if we all perceive the same things as beautiful and ugly, there is no problem. Designers just have to make things beautiful for all. But are we all really perceiving the same things as equally beautiful? We conducted a study in two parts. First, we created a computer vision system that would quantify images and say, would predict people's perception of colorfulness and visual complexity of an image. Because prior work showed that these two features are this is what we take into account when we decide whether something is beautiful or not. And then we conducted a study, we collected a lot of data and created a statistical model which allows us to predict from an image whether people will find it beautiful or not. And we also, in this model, took into account demographic variables such as age, education, gender, and so on, and looked whether these variables had an impact. So first, we created a computer vision model that would take a design like this, compute lots and lots of features, and then output predictions of colorfulness and visual complexity. And this model was actually very, very good at predicting human ratings. So what you see on the x-axis is what the system predicted. What you see on the y-axis is what people said, and the correlations were very strong. So we had a very good way of taking an image and automatically saying how colorful and how visually complex it was. Then we conducted a study on Lab in the Wild, which you should visit after this talk. And we collected data from nearly 40,000 participants from many different countries. Unfortunately, very few from Korea. And we looked at how people's sense of beauty varied with colorfulness and visual complexity. So unsurprisingly, we found that the images that we found most beautiful were neither very simple nor very complex. They were somewhere in the middle. They looked roughly like this. And similarly for colorfulness, we found images that were just colorful enough to be the most beautiful, on average. But we also saw some very interesting national stereotypes in the data. So for example, when you started adding too much color, the Germans felt uncomfortable. However, people from Chile, we couldn't have enough color there. It wasn't sufficiently colorful design in our set. I wanted to include data from Korea, but unfortunately, we didn't have enough participants from Korea. We do not because, we do not. I do not want to make predictions without data. So there's also evidence that what we find most pleasing varies with our level of education. The more education we have, the more boring we are. So we've built this system that takes an image and is able to predict how beautiful we'll find it. But also, as a byproduct of this work, we saw that age, gender, education all impact our sense of aesthetics. So let me kind of discuss some of the consequences of it. So look at this. This is a page from edX, a MOOCs, massive online open courses webpage sponsored by MIT and Harvard. The mission of edX is to deliver education to people who currently do not have access to it. So people who are poor, people who are from cultures where access to formal education is difficult. But notice, this design is hyper-optimized for educated Westerners, right? The complexity of the color choices are perfect for people with college education in America, and they will totally not work for people who lack formal education in Chile, right? So we're failing right at the very beginning. We are designing the educational resources in such a way that the people who most need them are the least likely to trust them, engage, and be successful with them. Another example. These are examples of the websites that women liked much more than men, and these are examples of websites that men liked much more than women. Notice that the two websites that men liked much more than women are both learning resources that computer scientists use either to learn or as a reference in their daily work. So we say we want women to participate in computer science, but we create computer science resources in such a way that women are just a little bit less likely to trust them, a little bit less likely to engage, and a little bit less likely to succeed. So this came as a big surprise to us. It really looks like visual design, like there are very big individual differences in what we perceive to be beautiful. And existing research tells us that these differences can have a very big impact on whether or not we choose to engage with these resources. Unfortunately, we are still working on seeing whether the visual design really does impact sense of trustworthiness and engagement, and we are still working on ways of automatically adapting visual design for people with different perceptions of what's beautiful. So with that, a very quick synthesis. most of us want something that want tools that are not very complex, but most of us want something different from our neighbors. In the current world, what we get is overly complex tools that have everything that anybody might ever want, but in the ideal tool in which we personalize and adaptively design the tools, we would have simple, nimble tools that are very good for precisely what we need. In the current world, when we design one interface for everyone, the people that the designer had in mind when they designed can use the interface very well, but people who are different in any way become much slower and much less successful. In the adaptive world, each one would get a design that is optimized for their abilities and needs, and the differences in their performance and success would be minimized. With the visual design, current tools optimize for the access to the information. Our tools try to optimize both for access to the information and for the quality of the experience. And in our current visual design, we often inadvertently discriminate against the people for whom we really want to design, the people that we would like to bring to particular resources or communities, and we still do not have a particularly good way of adapting to it. So, in conclusion, one-size-fits-all design is bad. It causes discrimination. I believe that when we talk about accessibility, it's not just about ensuring that people with disabilities or with different needs can access the resource. We also have to make sure that they have a similar experience, equally efficient, equally successful, equally pleasurable. And with my technical background, I believe that a particularly good way to accomplish it is to build systems that automatically adapt themselves to their users. There may be other approaches, but this is an approach that I've tested several times and I found to be effective, and I think it should be part of the solution that we create. Thank you very much.
Time for a few quick questions.
Yeah, and then I'm very happy to talk more over pizza. Giving others a chance.
So you mentioned it briefly that you haven't quite figured out how to do you want to do something similar as the disability customization for the aesthetics thing, and you haven't quite figured out how to do that exactly, I assume. But what are you kind of looking into in terms of I'd love to hear some more about that particular topic. Like, how are you going to fix the problem, basically, in your current plan?
So, it's a little tricky because we do not know whether people want the designs that reflect who they currently are, or whether they want the designs that reflect who they want to become. Right? If I, if I came for an exchange to Korea, maybe I wouldn't want designs that are optimized for Polish people. I'm from Poland. Maybe I would really want to be presented with designs that people around me consider beautiful because I'm here because I really want to immerse myself in the Korean culture and get to know it. Maybe people who come to edX want the designs that are appropriate for people with a lot of formal education. Maybe this is who they want to become. So we do not yet know whether design should really reflect people's current state of their aspirations. And also that it's tricky when different people see different designs. Because two people sitting next to each other will be seeing different things, and in case of disabilities, people do not mind it at all. They are perfectly happy to be interacting with different designs. People who do not even know that they are different from each other, they may be surprised to be presented with different designs. We do not know what impact it would have on people.
What about the gender thing? Because it's a bit more clear-cut with gender. I guess there's like transsexuality to contend with, but there's no real aspirations to move to the other gender. You probably don't have to worry about that. like, is this a main research focus of yours right now, or is it a kind of back burner thing?
It's one of the projects that is happening in the parallel. Right now we are really trying to quantify the impact on behavior and on the actual engagement.
Okay.
Like we want to see how much of a problem, the theory predicts that it is a problem. We want to actually see how much of a problem it is in the real life.
Thank you for the awesome talk. I'm really impressed about the optimization method that is based on the parametric model, I believe, of the scoring system of the how will the design will look like. I have the question about what sort of model that you have used to describe what can be different in the final UI, or what should be the constraints that what sort of models that should be there that cannot be changed or not.
So one important decision that I made, and this is something that you will find relevant, is that I decided to cast it as a discrete problem. So when you design the UI, you may think that the position of every button is a continuous variable, like it could be anywhere on the canvas. I decided that I would instead have discrete choices. So if somebody wants to communicate yes or no, it could be a toggle button, or it could be a checkbox, or it could be two buttons on top of each other. When I wanted to do layouts, I could choose between horizontal layout, vertical layout, or tab layout. And then within that, I would choose one of the existing methods for aesthetically pleasing design, such as maintaining alignment and so on. So I took away many of the decisions. My system only made very coarse design choices, like what type of a unit to use and what kind of layout strategy to use, and then kind of the details were kind of relegated to whatever was the default for a particular UI toolkit.
Thank you.
Okay, thank you for your talk. You mentioned that the user interface and the user will try to adapt to each other simultaneously, right? But then what if the user interface tries to change its interface like in the opposite ways that the user expects it
to? Till now in our work, the user would first make their adaptation. So somebody with big disability would choose what kind of input devices they wanted to use. So that would be their adaptation. So they would say, okay, instead of a mouse, I'm going to use a trackball, or I'm going to use something else. So that would be their part of adaptation. Then my system would say, okay, now that you've made your adaptation, let me measure what you can do with the choices that you've made, and I'm going to adapt to that. So they weren't adapting simultaneously. The user first made their choices, and then the system adapted to the choices that the user was willing to make.
Thank you. So I was wondering if optimization is necessarily the best approach in all cases. Okay, so I mean, it's related to the last question in that a lot of people try to learn and train themselves over time. So if you add the time dynamics, time dimension to the whole picture, right? So if you optimize to the current state of the user, they might not actually get a chance to learn and train themselves. So if you add the learning component, training component, or time component to the whole optimization equation or to your objective function, would that lead to different results? And if so, what are some possibilities?
So this is a brilliant question. Well done, Joe. You must have had an awesome advice. No, so Juho is making a very valid point. So when we interact with user interfaces, so many of you are familiar with Fitts law, right? So that describes kind of, given the physical layout, how quickly we can perform actions physically. But besides kind of motor performance in the user interface, there is also visual search. So we have to find the thing that we want to use, and then there's kind of the decision time. So we have to decide, which of the options in the user interface we want to make use of. So if I were to change the user interface constantly, so for example, people with Parkinson's disease change their abilities several times a day. So if I constantly adapted to them, they would have one interface in the morning, one in the afternoon, and another one in the evening. So kind of their motor performance would be optimized, but each time they would be confused and they would be spending a lot of time finding things. So good optimization for people with changing abilities or changing devices actually takes into account the variability in people's states and considers a trade-off between diminishing motor performance by not adapting perfectly to your state right now, and also the cost of learnability if I do make changes between one design and another. So we didn't do it for people's fluctuating motor abilities, but we did it for people who frequently change devices. So if somebody wanted to use the same application on a phone, on a laptop, and on a PDA and on a wall touch panel, we wanted to make sure that all 4 designs were both pretty good for each of the devices, that they made use of the screen size and capabilities of the devices well, but also we wanted to make sure that if I learned one design, I would very easily apply that knowledge to the other designs. So this is a very good question, and it is something that we can actually anticipate in the optimization process. It makes it more complicated, but it is possible. Maybe just one more question and then we have pizza.
Have you thought about incorporating existing designers in the process of optimization and machine learning to make better equitable interface design?
So I incorporated them in a different way. So what I showed you here was a system that learned the objective function by measuring a person's actual performance. I had another system that learned the objective function by asking designers. So it would show them pairs of examples that had the same function, but that had different visual design, and to ask the designer, which do you think is better for that device for that particular purpose? And the designer would say, this one, that one, that one, this one, this one, that one. And after about 50 questions like that, I would know that designer's style, and I would be able to produce new designs that pretty accurately reflected the style of that design. We also gave that capability to people with disabilities. So actually when we ran the study, we gave them 3 conditions. The standard design, one adapted automatically to their abilities, and one where they got to do this interaction, I prefer this one, I prefer this one, I prefer this one. So people without formal design training, when they were allowed to choose what they liked, the designs that they created, the objective function that they taught the system was not very good. When later on they got presented with the final designs that used the objective function that they trained with their preferences, they didn't like those designs as much as the ones that were based on their actual abilities. So it takes a little bit of formal training before you can really reflect on the goodness of the design. So we thought we could give users direct control over their designs, but it turned out that it wasn't a particularly good idea, but formally trained designers could communicate their knowledge very well to the system. Thank you very much.